Okay, we're going back to 2A.
Here. Okay, let's speedrun through 2A. Boom. Okay.
Okay,
Let's do this.
I'll just let you teach.
What's number 1? A linear combination.
What is a linear combination?
When you combine vectors in a way where you have scalars, where you can have any scalars which fall within F. You like add them together.
Yeah.
Yeah, that was a very bad explanation. But
every way you can multiply a scalar by your basis vectors.
Yeah, so if you have two things like that, you can just multiply both of them any which way and add them together and make this whole thing. Anyway.
Which is the span.
We're moving on to span. Whoa!
We are moving
The
on.
span is the set of all the linear combinations in that list of vectors. So basically, if you have all of those linear combinations in a set, that's a span.
Yes.
Let's go. I'm just so good at math.
So span is a set.
Yes.
That's what I'm taking away from this.
Of the linear combinations. Don't forget that part.
Oh, yes.
Yeah.
All the linear combinations.
Yes.
Of vectors in V. Nice.
Yes.
Oh, we didn't do this. Span is the smallest containing subspace. The span of a list of vectors in V is the smallest subspace of V, containing all the vectors in the list.
That feels pretty redundant to me, right? Or
is it?
is it?
I'm still trying to understand what it says.
Okay. I'll give you some time.
Thank you.
You're welcome.
What? All the vectors in what list? The span of the list is the smallest.
It's in the big V, right? Because the big V is the list.
Is it? I thought big V was a set.
Isn't set equal list? Like list is
No.
a set? No?
No.
What? Oh. Well, okay.
Does it?
I thought it was. Because it's just like the list of the things is the set. We actually found our true enemy, which was the math. It was actually just the English.
Okay, I'm gonna look that up. Yo, I'm currently learning linear algebra from Linear Algebra Done Right by Sheldon Axler. Sheldon
3 years
Axler,
now.
we bow down to him.
Your favorite guy.
Yeah, he's my favorite.
There's not a problematic difference.
Okay. It's an indexed set.
A set endowed with a function of I.
Okay, so I such that I maps to S. That's what that means.
Oh.
I don't know what I and S are.
Yeah.
S is your set. I such that. So your index maps your index to the set. So index I. That's a really redundant thing as well, because it's just saying the index in the set maps it maps every index to every element in the set. It's an ordered list. Okay. It's
So basically there's no
same
difference.
thing. Yeah, you're right.
I was right.
Yes.
Let's go. English
Math.
for the win. Woo!
Yeah. Or English genius right here.
Okay, so so basically all the vectors in the span of a list of vectors in V is just the list of the vectors.
Smallest.
Nothing more than that.
Yeah. Okay.
No secrets
So-
here. No secrets here. Okay, let's move on.
Span.
Polynomial, you can explain that one, buddy.
Okay.
I don't know, you can.
So a polynomial such that. So every z is your vector, and z squared is actually an abusive notation. So that's actually just one vector. So just think of that as one vector. So now you've got all of your variables in your polynomial, and then you've got all your coefficients in your polynomial. And you can change the coefficients to get every combination, creating every polynomial of that degree. And the set of all those polynomials is known as the whatever this is, polynomial set of all polynomials with coefficients in F.
Special P.
Yeah, special P.
Special P.
Sub M.
Also, like, why? Okay, so if this like isn't squared, why don't they just put the 2 like down there? You know,
Yeah,
as a subscript.
that's actually a really that's a
Like,
really
wouldn't that be more
easy
intuitive?
way to like solve that problem.
Yeah.
Although maybe it would be confusing because you're saying it's a polynomial, and then you look at it and it's
like not very degree-like in there, but
Yeah.
also at the same time it's not actually degrees, but
Yeah.
they're like, here's a degree of variable anyway.
yeah.
Yeah. Okay.
But you could do really cool stuff because this generalizes a polynomial into becoming a vector. So you can apply everything that applies to a vector to a polynomial now. Which I assume we're going to do
Or
in this.
vice versa, right?
Yeah.
Yeah. Cool. That's pretty sick. That means there's actual algebra at some point, isn't there? Okay. Anyway.
Is there?
I don't know.
I feel like this is more like the making of algebra. Like why it works.
Okay. You know what? I'm down. Okay. What else do we need?
Linear independence.
Linear
Did we do
independence.
that?
Yeah.
No.
Kind of.
Yeah.
Did we? Well, we didn't record it, so linear
Yeah.
independence is where you can have you can have scalars for the vectors in like the span, right? But it's linearly independent when if and only if the additions of all of them equal 0, if and only if all of the scalars coefficients of the vectors are also 0.
So
Did I miss anything?
additions of all of them, I'm just going to say, that means linear combination.
There we go. Yes.
So when the only way to make the linear combination equal 0 is by having all the coefficients equal 0.
Yes.
Yes. Okay.
That's a lot simpler than how I said it.
Okay.
Cool.
And why?
Why? It's. What do you mean? What? No, I'm just kidding. Okay.
What do you mean why?
What do you mean why?
It's just that way.
It's just how it is, man. Okay. Well, I mean, it doesn't work if it's not 0, right? I mean, okay, so they're all going in like different directions, right? Something
Yeah.
like that.
So if they, first of all, if you have 2 ways to make 0, that's not independent anymore. You've got 2 ways, so it's not one way anymore. And then how does that extrapolate into there being only ever one way to combine them to get every vector in your space? Why does that condition of only having it equal 0 extrapolate to...
Extrapolate?
Well, like, how does that connect? Why can you just check that it's all zeros? That there's only one way to make it 0.
Oh, all zeros.
Why don't you have to check all of the combinations?
Because I mean, like, okay, so if they're all independent, then you don't need to.
All independent.
Right? Like, okay, so because
Yeah.
if they're like slightly related in some way, right? Like they're going the same direction is how I'm like thinking about this,
Yeah.
right?
So
Then they in some way
So
and
you've got
capacity,
two in
if you
the
have
same
specific
plane.
scalars that aren't 0 at that point, then they'll equal 0 somehow, and that doesn't work. So they have to be like different
kind of.
in order for them to have them all
I think-
times 0 equals 0 in their linear combination.
Yeah, I kind of get that.
Yeah, I feel like I'm
Okay,
spouting
let me try
nonsense.
to explain or like reinterpret what you said,
Mhm.
how I understand it.
Mhm.
So you're saying you've got linear independent vectors pointing in different directions. So this is R3.
Mhm.
And there's only one way to make it 0, and this is only possible if all of these are 0.
Yeah.
Because otherwise you could have 2 in the same plane, and all you have to do is make this one the negative of the other one and add
Yeah,
them together. And then
exactly.
there's more than one way to make 0.
Exactly.
Okay. And then how does that why does that mean that there's only ever one way to make every element, every
I don't know.
like,
That's yeah. So
vector?
like that's like the contra thing. That's like the if, or like the only if, and
Yeah.
then the other one is the if, which
Maybe
I don't know
you have
yet.
to go through the proof to do that, but I'm sure there's a logical explanation.
It works because I mean, I don't know,
because
1, 0. Yeah.
no, it makes sense, because if the only way to make 0 is by having them all equal 0, then they must be pointing in different directions, which means that there's only, because it's a different direction, you can never make this vector by combining two other vectors in a different way.
Yeah,
Does
yeah,
that make
yeah.
sense?
No, that makes sense to me. Yeah.
Yeah.
I think I get it.
That's why there's only one way to make every vector if they're linearly independent.
Yes.
And the linear independence comes from them all being 0 when they're all 0.
Yes.
Okay.
Okay. Moving on.
Weird.
Linearly
rambling.
independent is when it's not easy peasy.
Yeah.
Let's go.
And then the lemmas and theorems. I think you can
Lemmas.
explain that.
Right. So when you have a span, when you have spanning, right? I was the only one who heard that, right? So spans, right? They like can have like a lot of different vectors, and out of that, there's some vectors that are called J, and because they're called J, because if you remove them, they can still exist within that span, because you can kind of derive them from the other existing vectors that are already in that list.
Actually, I had a cool way to explain that as well.
Yeah, go for it.
So if you think of 3 vectors in the same plane. So if you, doesn't matter how you order them in a list, if you remove one, you can always make it from these previous vectors in the list, no matter how you order it.
Yeah.
Which is why the previous vectors can make the next vector
Yes.
in the span.
Right.
Yes.
Yeah, so basically that means that they can just kind of be taken out without the span actually being changed.
Yes.
So, yeah, that's it. You can basically reduce spans.
And this is used in our other stuff that we have to do
Yes.
later on.
Exactly.
Okay, and then this is the confusing one.
Right. So, okay, so we have J, right? We love J because that means that the spanning list can be reduced down like a bunch until you're only left with the linearly independent list. So you can only have the vectors that are linearly independent, which means that the length of the linearly independent list always has to be less than or equal to the length of the spanning list. It can't really be more than that.
Yes. Good theorems.
Woo! Let's
This
go.
is like
I'm learning so much. Wow.
epic.
Damn. Okay, is that it?
Is there more?
Oh, every
A
subspace.
finite dimensional subspace is finite. What? Okay. I don't know why we need to prove that. But it's math. You prove everything. You can't just say
Oh, it's another step J. Oh my gosh.
Yo.
Yo, I love this guy.
Are we done? Yay.
Are you done with that? Problem solving.
Okay.
Next. Okay, so bases.
Read basis.
But not like the chem kind of bases. A list of vectors.
Wait. Oh, you're reading the top basis.
Yeah. I don't know why they're different. Okay. A list of vectors in V that is linearly independent and spans V. Doesn't every linear independent thing span?
Not necessarily.
Not necessarily. Why?
Because think about the unit vectors. So 1 0 0 0 1 0 and 0 0 1, right? That only spans R3 3-dimensional space. It doesn't span 4-dimensional space.
Oh.
You have to have another perpendicular vector like that.
Okay.
Through time or whatever.
I see. So it has to
So
go in all four directions or dimensions.
Yeah. So it can be. These are linearly independent because no two. So linearly independent. The visual explanation is that no two can create another.
Mm-hmm.
So if you have all three vectors in the same plane, they're not linearly independent because you can use these two to create this vector.
Right.
Yeah.
Okay. Makes sense.
Yeah. Yeah, so a basis, I just remember it as the unit vectors in each direction.
Mm-hmm.
But
and that's
you've
the
got,
standard basis. There we go.
Yeah. Yes. That is the standard basis.
1, 2, 3, 5 is the basis of F2.
Is it?
Is it?
Is it? I don't know.
It's in the textbook, so it's got to be right?
I guess. It's so weird how it says F, because F includes complex numbers, and I don't understand how this can include complex numbers. Actually, yes, it does, because if you have a scalar multiplying it, like the scalar is complex.
Then you can just make it all complex. Yeah, okay.
Okay.
I see that.
That makes sense, yes, yes. Algebra is really cool.
Wait, so why does B work? Why does this
basically
F to the 2 F squared, but it's not actually F squared, right?
So two-dimensional space.
Okay. Oh yeah, so
But
two-dimensional space.
Yeah.
But then.
So all they have to do, I guess, is point in different directions. And since they're not, it's two vectors, so they're not pointing in the same direction, so they must be pointing in different directions, right?
Okay, because it's like just a one plane.
Yeah.
Two-dimensional plane. Okay.
Yeah.
Cool.
And then you. What?
Right? I don't know. Yeah. They're just in different directions somehow.
Yeah. So you can reach every combination of a complex number and a real number and a complex and real and complex, because you multiply scalars to create every element in that space.
Okay.
Right?
Makes sense.
I think so. Not too sure.
Right.
This is so weird because I'm thinking in three-dimensional space.
But it's just two-dimensional for this one. So there's that. Okay, but this one, C, doesn't span because it's, I guess they're going in the same direction somehow? How does that work?
Are they? Let's see. Okay, it's linearly independent in F3, but it doesn't span because it's only two vectors, and you can only cover a two-dimensional space.
I see.
Nice.
And then the thing goes here. It's not in, because there's three, which means that two have to at least like cross somehow. Is that how it goes? If we take last time's logic to this one?
Yeah, kind of. Right. It's because there's an extra vector that's not needed, so it's not linearly independent. That's what it says, yes?
Yes.
Yes.
I believe this.
Okay.
Yes. Makes complete sense.
Yes, complete sense.
Yeah, I don't get this notation still, so that's okay. Let's just get the rest.
Which one?
Oh, just like this, this whole thing.
Oh, that's
Chapter
easy.
1. Didn't actually do, kind of.
That's easy. It's just, so curly braces mean set.
Yeah.
And then whatever's in it is a generator for the set.
Okay.
So that thing generates every element in the set.
Oh, okay.
So x, y, so you've got a vector. So you know every element in your set's going to be a vector.
Falls within F3.
Yeah.
And then x and y have to be an F.
Yes.
Gotcha.
So it's, all the vectors that satisfy that.
There we go.
Nice.
Let's go. Just let it go, please. Oh, the polynomial.
I don't want to do that.
Oh.
Oh yeah, this is so cool. It's a basis of the nth degree
Ah.
polynomial.
Because all the lists of vectors are going in right ways or whatever. Is that how it goes?
Well,
I guess so, right?
we can't.
That's what Z is, right?
I can't think of this in space terms because it's not. But you've got different variables, and it spans it because every linear combination will create every element, right? And it's linearly independent because you can't create Z to the M using yes, because you forget about multiplication. Multiplication doesn't exist.
No, yeah.
Because linear combinations are scalar multiplication, but it's addition of Z's. So you can only add Z's. And you can never add 2 Z's to get a higher degree polynomial.
No.
Wait, that's it. You can't add 2 lower degree polynomials to get a higher degree polynomial.
Yeah.
You can only subtract and get lower degrees.
Like what?
Because if you have x cubed minus x cubed, that's just 0.
Oh, yeah.
But you can never go above x cubed.
Oh, yeah.
By adding.
Yeah. Oh, I guess that's the same concept here. Basically, is what you're saying. Okay.
Basically.
Basically.
That's great.
Oh, you're so funny. Okay.
Okay, but the fact that happens to be a basis feels like it's just pure coincidence. But it's so nice.
It's nice. You know what? We take it.
Yeah, we take it.
It's how
like,
math goes.
In a parallel universe, adding, 2 quadratics could possibly go to a higher quadratic, but no, not in this universe.
That's gross.
That never
I'm
happens.
glad I live in this universe where that doesn't happen.
Yes.
Okay. Fn has many other bases. For example, these both are bases of, okay. So there can be more than one basis for an F.
Which one are you reading?
I don't know, I'm just reading like right below the thing. Anyway.
Oh, here.
Yeah. I read textbooks books. Just go to the next thing.
No, that's
I don't think that's how you're supposed to do it.
That is me.
No.
Next result helps explain.
Okay, so the criterion for basis. So this is what is required for basis.
Yes.
If and only if. Our favorite boyo. Okay. It's okay. So a list is a basis if and only if V within V can be written in the form of that, where all of those scalars are in F.
Okay, that seems really trivial.
Okay.
Wait, what?
If only if every vector
can be written uniquely in the form. So what?
I don't know.
There's only ever one combination of all these that can generate a vector.
The basis?
Yeah. What is it trying to say?
I'm not too sure.
So a list,
if only every V can be written in the form of that, where, but then what is that V? Oh, can be written uniquely in the form. Oh, so it's like the V, so every vector has to be like a combination of the other vectors by scalar. Is that what I'm getting
how does this look different to being linearly independent? Wait. Isn't that just linear independence that you can only write? Oh no, it's not.
Because you can technically probably do this and not be linearly independent, right? Probably.
Maybe.
Because it doesn't have to be necessarily unique. I don't know.
don't know. I feel like skipping this because it feels like it's just another way of saying it's linearly independent.
Okay. We can move on then.
Yeah.
Let's proof. Whoa.
Spanning list contains a basis.
Every spanning list in a vector space can be reduced to a basis. Okay. So basically, every spanning list is redundant and we don't like them. Or I don't know.
Yeah. It's basically.
So, but not every basis is linearly independent because.
Wait. No, every basis is linearly independent.
Oh, okay, gotcha.
It always spans and is linearly independent to be a basis.
Okay. Oh, okay. So
Yeah.
that's like the definition of basis. Easy.
Yeah. So if you have a spanning list and it's not linear, if it's linearly dependent, you can always, by that theorem that we did, you can always remove vectors until it's independent.
I love
and
condensation.
it still spans it.
I love condensation.
Condensation.
Condensing.
Yeah. Condensation.
I don't know.
Is that what it's?
I think so. We're just gonna assume like it is.
Another word for meaning for it.
I don't know. I can't think of one right now. Okay. Anyway, every finite dimensional vector space has a basis. Let's go.
They're so simple statements, but when you're asked to prove that, I'd be like, what?
By definition.
By definition.
A finite dimensional vector space has a spanning list. The previous rule says the spanning list can be reduced to a basis. Okay.
Yo. Okay. Big brain moment. Is it? It seems so trivial.
Yeah.
Yeah.
Oh, okay. Because every finite. Okay, so the definition of the finite has a spanning list, and spanning lists can all be reduced to bases. So therefore,
it
x
has
equals
a
y,
basis.
y equals z, etc. Anyway. Okay.
Yes.
Every linearly independent list of vectors can be extended
to a basis.
So
Okay.
every basis
Extended.
is linearly independent, but not every linearly independent thing is a basis.
Wait.
Yes. Okay.
What did you say? Every basis.
Every basis is linearly independent, but not every linearly independent list is a basis. Yes. Okay.
Okay.
Yeah, because we talked about that earlier.
Yeah.
Easy. Okay.
Linearly. Do you know what extends means?
Does that mean you can just? No, I don't.
No. It means add vectors to it.
Okay.
So you have a list that is linearly independent, and this is saying that you can always add vectors to make it become a basis.
Okay.
If it's linearly independent.
Seems legit.
Yeah. This is epic. This is like a speed run of chapter 2B.
Let's go.
Oh, okay. This one's got a really intuitive way of thinking of how it works.
All right, shoot. Suppose V is.
Never mind. I was thinking of 2C. The last thing
Shucks.
in 2C.
Okay.
This one's just, I don't know.
Every subspace of V is part of a direct sum equal to V. Okay. Kind of forgot what direct sums were. Okay. Suppose V is finite dimensional and U is a subspace of that, then there is a subspace W where V is U plus W. Direct sum W.
Yeah. A direct sum is where there's only one way to write your resultant vector.
Oh, okay.
So like if you have 0, 1 and 1, 0, there's only one way to make 1, 1.
Okay.
Just by adding them.
Gotcha. Yeah, okay, that seems intuitive enough. My mind can just gloss over that one.
Yeah.
If I want to keep speed running. Unless
Here's
there's
the
anything
subspace.
interesting about that.
I guess, yeah, it's kind of interesting. The fact that there's always two. It's basically saying there's always two subspaces. No, it's saying you can choose any subspace of V, and there will always be another subspace of V that you can add to it to get V, which makes very intuitive sense, right?
There's always a complementary subspace.
Yeah.
Like angles. Whoa. My small brain cannot handle. I need to dumb it down to like 8th grade level.
Let's go.
Wow, we reached the exercises. That's crazy.
Yes, very crazy.
Speedrun. Oh my gosh.
All vector spaces that have exactly one basis. This was kind of fun to do. Can you think of like a guess?
Like the approach that you can do? Exactly one basis.
Okay.
Okay. Exactly one basis. I would assume they'd have to be like small, right?
Very small.
Very small?
Yes.
Probably like, yeah, if it's a vector space that has one basis, then it's gotta be like one-dimensional, right? Or is it?
Technically, except, so what is a basis?
It spans and it's linearly independent.
Yes. And what does it mean to have, how do I put this, exactly one thing that would span and be linearly independent? So you've got a list of vectors. So basis is a list of vectors. And then you only want one of those. So what's the condition? Okay, think of the inverse. What's the condition that would get you to have multiple of those bases?
What if we just have like a 1-0 kind of moment?
Yeah.
Yeah?
Yeah, we could do like 3-dimensional.
Yeah.
So this is a basis. You can multiply them all by 2, double the length. That's also a basis because they're linearly independent. They point in different directions and they span.
Yeah.
And you multiply by 3, by 4,
so
by
etc.,
5.
etc.
So to
that's...
have one basis, you can't.
It has to be 0 at some point? Or...
Yes.
Yeah. Okay.
Because if you multiply 0, you just get 0.
0. Okay. Let's go.
So all vector spaces are.
Is it just like that blank set 0
yeah.
thing? Okay. Yo, cool.
I actually found something really cool when I did that question. There were actually an infinite number. I don't remember how I did that. I might be wrong. To be.
Oh, you actually are doing just like 1, 4, 8, huh?
I am.
Are you doing like all of them or just 1, 4, 8?
Just 1, 4, 8.
Okay.
I originally intended to. All vector spaces with exactly one basis. What am I saying? Are the 0 vector spaces. Oh, a 0 vector. Okay, this is why there's multiple. So 0 vector space can be just 0. It could also be 0, 0.
And it can be 0, 0, 0.
Yeah,
okay.
So that's why there's an infinite.
Or the 0, okay.
Yeah, all the 0 vector spaces. It makes sense once you understand it.
Yeah, but when you don't, you're just like, vector spaces with one basis are actually 0.
Yes.
Vector spaces.
Yeah.
Makes sense, actually. You're fine.
Everything's good.
All is well.
A linearly independent list of the right length is a basis. Oh, wait, what are we doing right now?
Oh, is this on C?
Oh, we're doing dimension? Do you want to do more questions or?
I'm down with whatever.
I like speed running. It's easier than trying to remember how to do a question.
Heck yeah. Okay, so dimension.
Yes.
Any two bases of a finite dimensional vector space have the same length. Okay.
Oh, you're reading that.
Wait, so of like the same vector space, right? Yeah, because there's like two different bases for that vector space, and they have the same length. What does it mean to be length? Like the length of like the number of vectors in the list, right?
Yes.
Okay,
yeah.
Gotcha.
So your basis is a list, and then you have the length. Yeah, this is kind of weird wording. Any two also means all of them have the same length.
Yeah.
And it says later in the chapter that length is known as the dimension.
Oh.
Yeah.
Oh, okay.
And I think the reason why they called it dimension is because of the standard thing.
Yeah.
Because you have that many vectors, and that's three-dimensional space.
Cool.
But it's interesting when you do polynomials. So,
Okay.
what do you think a polynomial's dimension is? Of n degree.
I mean, like, what? Don't they have, like, different degrees as, like, the polynomial goes through different terms? Or am I just tripping on that?
Yeah, they do. Except if you go, let's say, an nth degree polynomial consists of previous degree polynomials, is what you're thinking, right?
Yeah.
Yeah, except if it's the nth degree polynomial, so what is the basis's length?
Well, like
Or
the
that.
degree of the polynomial, right? So, like, n.
Is it?
In that point.
Think about it.
Is it not?
It's really weird.
Oh, is it +1?
Yeah.
Because of the scalar?
Yeah.
Oh, okay.
So it's the degree of the polynomial plus 1 is the dimension. And that's always the same because all the bases have the same length.
Okay.
Like, that's a weird thing, and I actually read the proof and I don't remember how it works. Like, that's so weird.
Yeah, that is funky.
All the different bases.
It just has to be +1 for some reason.
Yeah.
Okay.
I mean, three-dimensional space, it's intuitive, I guess. Because you just need three. It's always three that are pointing in different directions. Because if you have four, then you can always make that fourth one with the others. So you have to eliminate that for it to be a basis.
Okay.
So they always have the same length.
Yes.
I guess it makes sense.
Oh yeah, I get that.
Right. Speed run entire chapter 2. This is so efficient.
This is so great. I don't even need to look at the textbook before we meet up.
Yeah.
Just gonna run through this.
Yeah.
Easy peasy. Okay.
2.38.
If V is finite dimensional and U is a subspace of V, then the dimension of U is less than or equal to the dimension of V. I mean, since the U is technically smaller with the subspace, does that make sense intuitively?
I'm still like parsing what it says. Yeah, how can the dimension of a
be different though? Wait. Because don't they have like the same dimension? Oh, well, that's gonna be equal, right?
Yeah. I mean, it makes sense. Because a subspace is. How can a subspace of a vector space have a dimension that's greater than its contained like parent space? That made no sense.
That's funny because it can't.
Haha.
Yeah, I don't think that would be possible, right? Because like subspace
always
has to be smaller.
Yeah, like so you got three-dimensional space, and you've got two-dimensional space, which is a subspace of three-dimensional space.
You can't really stretch that into four-dimension.
Yeah.
Yeah.
It's never gonna be. These are so like straightforward, intuitive. They're just written weird.
Suppose
2.39.
So the linearly independent list of right length is a base. Okay. If V is finite dimensional, then every linearly independent list of vectors
in
V
is
with length dimension V is a basis of V. Okay. Right. So, like for example, if you have the three things, then it has to be. If the list is 3 long, then it's a basis. But if it's 4 long, then it's not. Because the 3 is like how long the dim has to be.
Yeah.
Okay.
I think I can explain the proof for this one.
Yeah. Go for it.
So, yes, I have the floor. Now I can't speak. So every okay, never mind.
Stage fright?
Yeah. time to like figure out how I'm gonna say it. Oh, okay. Actually, it uses a theorem that I need to remember.
Is it from 2.33?
It might be, yeah.
Oh, that's all the way in the previous chapter. Ew.
Of the right length. Okay, so follows from the theorem that every linearly independent list can be extended to a basis. So, do you remember that every linearly independent can be extended to a basis?
You can just
Oh, yeah,
add
have
new
it.
things.
Okay.
Yes.
Yeah.
Right there.
But because the dimension is correct, you don't need to add anything. So by definition, it is the basis.
Seems legit.
Yeah. That's like logical.
Yeah,
nightmare.
so it
But-
already has the number of vectors needed
Yeah,
for it to be a basis,
Yeah.
is what you're saying.
yeah, because if the dimension is correct and if it's linearly independent, and this says that says that every linearly independent list can be extended,
Mm-hmm.
or it does extend to a basis, like that's fully concrete, that must happen,
Mm-hmm.
then you've got the basis because you can't extend it.
Yeah. Yeah.
Because
Okay. Yeah. Yes.
okay, because
Yes.
the dimension is always the same.
Yeah. It always is the same length.
Yes.
Wow.
So if you
Crazy.
extended it, it wouldn't be.
It
It'd
wouldn't be a
be-
basis.
Yeah, it'd
anymore.
become
It'd be
maybe spanning, but it'd be linearly dependent,
yes. Okay.
I guess.
Yeah.
Yeet.
Yeet. Let's
Yeet.
go.
Okay.
Okay.
Alright, which one are we doing now?
Where were we?
We were on 3-9. And it jumps to 4-2.
Let's go.
Where's 4-0? Oh, okay. Never mind.
It's an example. Okay. So 242.
2-4-2.
Spanning list of the right length is a basis.
This is the opposite now. Okay.
Okay, so then
So if
every spanning list of vectors in V with length of the dimension is a basis. Huh. Even if it's linearly dependent?
Okay, let's think about this.
Okay.
So if it's spanning,
Mm-hmm.
but it's the right length, then there's something that's going to say that it can't be linearly dependent, so it must be
okay.
independent. And that thing is 2.31. If we go up to
Oh,
2.31.
Boom.
Okay, so every spanning list contains a basis.
Mm.
So if... Okay, this is the exact same reasoning. If it's spanning
Mm-hmm.
and it contains a basis, but you can't make it any smaller because the dimension must be that length,
Mm-hmm.
then that must be the basis.
Oh, okay.
Yeah.
Okay.
Because spanning list contains a basis, but it can't be anything smaller than the actual length of the basis.
Right. Okay.
Right?
Mm-hmm.
Okay.
Okay, so it can be reduced, but just like it can't get smaller
It's
than
reduced
that.
by 0.
Yeah.
Something like that.
Seems legit, I guess.
Yeah.
Okay.
All this logic. It's actually really simple. Like
Yeah.
if you changed how you worded all of this, I think you could explain it to a 5th grader.
Yeah, if you like did this in layman's terms rather
Yeah.
than finite dimensional
Yeah.
basis.
It feels easier
Set.
than calc,
Yeah.
at least to me.
Conceptually, I mean, like it makes
Yeah,
sense
like it's
if you
pictures.
understand.
I like pictures. I don't like solving an
Dude,
integral.
when Prof. Juan started drawing stuff, I was like, oh my gosh, it makes so much sense.
Yes.
Okay.
Yeah. 2 point. Why does this one? So examples get numbers, but proofs don't.
Yeah, because the proof is right.
Interesting.
It's right below the thing. Right below the thing. Right below
Yes.
the 2.42.
2.43. Let's let's go speed run. This one's the nice one. It's very intuitive.
If U1 and U2 are subspaces of a finite dimensional vector space, then the dimension of U1 plus U2 equals those two minus the combination, like the U1 intersection of U2.
Does that make sense?
Yeah.
Yeah.
Yeah. It's like probability.
Yeah.
It's like replace that with like problem. It's easy. Okay.
Basically.
Yeah. Okay, yeah, that makes sense.
Yeah, because I don't know how I think about this more rigorously, because all I'm thinking is you get dimension 1, dimension 2, but you counted stuff twice, so you take out the intersection and then there you
go. Easy. It's just a Venn diagram thing. 7th grade.
Yeah.
There you go.
Yeah. Except this proof is the longest one in the entire chapter.
I mean,
it takes up a page.
Oh my gosh. I mean, like, I guess, like, I don't know. It's like, if it's simple and intuitive, it's, like, hard to prove. From my experience of, like, not actually proving anything since 8th grade. But,
yes,
you know, that's what I've garnered.
Prove root 2 is irrational.
It just is, man. I don't know knowing what's going on.
Oops.
Cool. Clearly span blank 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 contains U1 and U2 and hence equals that. So show that this is a list of a basis of U plus U2. We need only show that it is linearly independent to prove this, I suppose. I don't even know where I'm reading either. Oh, it's
dimension.
Like it's partly through.
Are you
I'm
reading
just like,
the proof?
Yeah.
Why are you reading the proof?
Why not?
Also, this looks hectic. Look at how many polynomial questions there are. Oh. Integral.
No.
A polynomial degree 4 of the real numbers such that the integral from negative, and we have to do this one as well.
No.
From negative to 1.
Have you done? Like, so I'm guessing you haven't done this one yet, then.
No, this is the only one I haven't done. We can try struggling.
I don't know how.
I won't be able to explain anything though.
Okay. So P.
Oh, we're going straight to 8.
Oh, I don't know. You haven't done 1 through 4, 1 or 4 yet either.
No,
okay,
I haven't done any of them.
Gotcha. I mean, I haven't done anything either. So finally equals. Let's go. Okay, suppose V is finite dimensional and use a subspace of V such that prove that U equals V.
Well,
see, it's just intuitive,
this one's easy,
and that's why it's like.
Right.
I mean, yeah, so it's like the dimensions means that the...
Don't we use the... I'm getting like a rush of all the theorems and I don't know which one to use. It's the same thing, like we can't make it any smaller, so it must be equal. That idea, right?
Oh,
like
we can't make it any smaller?
Basis.
Right, yeah.
So suppose it's finite dimensional. Okay, yeah.
So we would first use like the dimension thing means that the basis lengths have to be equal.
Oh,
right?
Yeah. Wait.
Can we use that or no?
Yeah, so the dimension for a vector space is always the same, right? So you can't have a different... So, wait, how do I put that into words as in if you have a subspace of that and the dimension's the same, then it must be the same
space because you can't
have any different length.
Yeah, any different lengths of like vectors
Dimension,
because then it
basis.
Wouldn't actually fall in basis.
Yes.
Because then it would actually fall into where it would go.
Wait, dimension. Okay, what is dimension again? The length of the basis, right? So you have length of the basis. Where is this going?
Yeah, the length of the basis has to be the same. And if U is a subspace of V, that means each of the vectors. So that means that they have the U and V automatically have the same length.
Same basis as well.
Basis, yes.
Which means they're the same vector space.
Yeah, because then there's got to be something about a subspace not being able to like be outside of the space that the vector space is, right?
Which means it contains the same elements. Okay, that's where we have to prove, right? Because
I think.
Okay. Can a subspace? Why can't a subspace contain different elements?
because then it wouldn't be a subspace. Circular argument. Easy, easy.
But then there's stuff outside of what? But the subspace. Okay, subspace is like, this is my space, my laptop length.
Mm-hmm.
Subspace is from here to like there.
Mm-hmm.
What about these things? Oh, but the
But the
length is the
dimension,
same, which means it
yeah.
has to contain all of the vectors.
Yes.
Nice.
Let's go.
Let's go. Very rigorous formal.
Dude, I was like,
Just like
imagine writing all of
waving
this stuff.
your hands all over the.
Yeah, I'm like, da. Yeah, it's like, I don't know how.
Sign language.
Just like writing it down sounds like a pain. But anyway.
Yeah.
Cool. So that means we've covered chapter 2 with me.
Yes.
Yay.
Should do like a. This has been a recap.
This has been a recap.
Has it?
I don't know.
This has been a recap of chapter 2.
Sure, this was a summary.
High
This was a
five.
crash course speedrun.
Yeah.
Woo! Okay.
Not really speedy. I wouldn't say it's speedy.
I don't know, if we're learning
I
a
mean,
whole chapter in like an hour.
An hour, that's pretty good.
That's not too bad, right?
yeah. I can't wait to do 2C question.
8.
Well, yeah,
Okay.
8 and 4, because those are like the cool things you can do with polynomials now. I want my phone.
There we go.
You know what? Okay.
I thought we were cutting off our faces.
I don't want to cut off our faces. That would be very painful.
Okay, that should be good.